Okay, so I drew our diagram just because I wanted to make it a little clearer and I wanted to talk about it specifically. Okay, so if you remember when we did this diagram a few days ago, the green were the crests and the pink were the troughs, or vice versa. And so everywhere two green were crossing, you were getting constructive interference. Everywhere two pinks were crossing, you were getting constructive interference. But everywhere a pink crossed a green, you were getting destructive interference. And the result was that if this was light and you put a screen out here, so this is my screen here, then this central these would be bright spots, points of maximum constructive interference, and this one is called the central max. This would be the first max, the second max, and the same on the upper side, first and second. And in between would be dark spots, because look, this is pink crossing green, destructive interference. So this would be the first minimum. Max stands for maximum, by the way. And the first minimum on this side. And then the second, whoops, this would be max. And this would be min. Okay? And it would be symmetrical. The distance from the central max to the first max, we call this distance x. Okay, and it'd be the same down here. The distance from where the sources are to the screen, we call this distance L. And the distance between the two sources are D. So those two sources, if it's light, they would be like little slits. If it was sound, they could be two speakers. Could be cell phone towers, okay? But whatever they are, they're the sources that are emitting these waves. Now, just as we ran out of time on that last video, I was saying if you were to draw a line from, let's say, the two sources to the first maximum. So let's see if I can do this without a ruler. Nope. Okay, imagine that's straight. The difference in these two lengths has to be a whole number of wavelengths. So if I measured this length and this length, it would be the same, and this would need to be a whole number of wavelengths here. And if it's going to the first max, it would be one wavelength. If it was going to the second max, it would be a second wavelength. This angle here, and I got to get the right angle here, and this angle and the line in between, and the angle okay, so the angle between this guy and this guy. So this theta and this theta are the same. And that becomes important. So this would be, if this is D and this is theta in here, then this little piece will be D sine theta. And you don't have to worry about this. I just want to show you. So if we look at the big theta, this is x, this is L. Tan theta is equal to x over L. If we look at the little theta, then we will have sine theta is equal to d over lambda. D over lambda, right? D, this side. Oh, no, sorry, wrong way. Lambda over D. Get it right. Lambda over D. And when we're talking light, like we're talking major, tiny, tiny, tiny. And if you were to pick up your calculator right now and take like the sine of 10, and then take the tan of 10, you will find that they're almost identical. For small angles, sine and tan are almost equal. And when we're talking about light, these are very tiny angles. And so what this gives us then is that since sine and tan are equal, then lambda over d equals x over L. Okay? And that's what all that mumbo jumbo is in your notes if you printed out the sheets that I gave you. It's just deriving that lambda over d is equal to x over L, where x is the distance between the bright spots or fringes. L is the distance from the slits to the screen, or the sources to the screen. Slits if it's light, sources if it's something other, to screen. D is the distance between the sources, or slits. Between slits, so like how far they are apart. And obviously lambda is the wavelength. Now for this to work, the light has to be what's called monochromatic, has to be a single wavelength, okay? And then obviously if I move the screen in, the axis will get tinier, right? The screen moves in. If I change the lambda, it's going to change the axis if I keep the D and the L the same. Okay, so this is called a double slit diffraction interference pattern. Now the cool and perhaps strange thing is the same thing can happen with a single slit. And you might find that peculiar, like how can a single slit interfere with itself? But for a single slit, why does my thing do that? The camera flips around. For a single slit, if I put my screen back here, most of the light will go straight through. My camera keeps flipping around. I don't know if it's screwing up the thing on your screen or not, so I keep trying to flip it back. So most of the light will go straight through, and you will get a really bright central max, thick central max over here. But around the edges, it will diffract. And eventually, the diffraction from the two edges will interfere. And so you will get tinier bright spots. First min max and second max out here. But they will be significantly smaller than what you would get for a double slit. Okay? So a double slit, they do get weaker as they go out, but most of the light, because it's traveling straight through, will be at the central one, and these ones will be significantly weaker. So the same equation works for a single slit. So this is single slit. The same equation works, except instead of the small d, which is the distance between the slits, we will use a capital D, which will be the slit width. So the equation becomes lambda over capital D is equal to x over L. Okay, where this is the slit width and everything else is the same. Now, some of you might have a hard time remembering what goes where, so it's really easy. Remember I told you that lambda was really a dinosaur standing on its back legs, eating the branches off a high tree. So as long as you can see that lambda is a dinosaur, then this is lambda is a dinosaur, and they are extra large, because dinosaurs are extra large, especially if it's a Tyrannosaurus rex that's eating a lot of leaves. Okay? So same equation really, we just use the capital D for the slit width. Now also on your notes, if you printed it out, you would see a spot that says intensity of the diffraction patterns. And it goes back to me saying these ones, the single slit has a much wider and brighter central band. So the next thing we're going to do, and we'll probably come back because we're out of time, we'll take a look at the two diffraction patterns for a single slit and a double slit, okay?